My name is Eric Breyer. I'm a computer science student at Rice University and a former student at Westwood High School. This is the WC1308-EAL breadboard computer. It's a fully Turing-complete computer built entirely on breadboards out of discrete TTL components. I originally built this computer with friends Luke Mason and Alexander Nucitelli. We were going off of Ben Eater's design. Since then, I've improved the computer, including adding more RAM, more instructions, an automated programmer, a stack, and an LCD display. The first iteration of the computer was very similar to Ben Eater's design, just with an expanded memory from 16 to 256 bytes, and an expanded instruction set as a result. This was still technically Turing complete, as we had conditional jumps and everything else, but without functions or a stack, we were fairly limited in the types of programs we could make. Some cool things we were able to do during this period were the Fibonacci sequence, calculating the largest divisor of a number, and calculating the square numbers using the idea of a constant second difference. The computer uses an accumulator architecture type design with a few major modules, the first of which is the clock module, which sends pulses to everything else to keep everything in sync. Next is the random access memory, or RAM module, and the memory access register. These two components allow the computer to store data and retrieve it again for later use. This is the program counter, which keeps track of what step of the program we're currently on. Next we have the general purpose registers, which allow for short-term storage, and the ALU, which handles arithmetic operations. This is the output register, which sends its contents to a 7-segment display. It allows for display in either unsigned or 2's complement modes. Lastly is the control logic, which tells all of the modules what to do on this step of the program based on the current state of the computer, including what the current instruction is. Originally, programs had to be inputted in the computer by hand using dual inline package or dip switches. This was very cumbersome, time-consuming, error-prone, and impossible to debug. To make it a little easier to write programs for the computer and input them, I got an ESP32 that allows you to connect to it over Wi-Fi and send it the bytecode. It will then twiddle all the correct GPIO lines in order to put the right data in the correct addresses. From here I added a custom assembly language to increase the ease of making more and more complicated programs. And then I also created a parser and assembler in C# to translate the custom assembly code into machine code and send that to the microcontroller to program the computer. The assembly language and assembler made the computer much easier to program and is now an invaluable tool for the types of programs that I'm inputting. I do want to note that even though the ESP32 is on the breadboards, it only helps in inputting the programs. The programs are still completely run by all of the discrete TTL components. The next step in expanding the power of the computer was adding support for functions, which necessitated adding a stack, which is a special type of memory where you put things on top and then you can pop them off. It's a first in, last out data structure. So this required 2 more modules that are down in the bottom right. There's the stack pointer, which keeps track of where we are in the stack section of memory, and the offset register, which allows us to grab things off of the stack relatively. So when we call a function, we push input parameters onto the stack, and then the function knows where those are. So it might know that its first input parameter is at the stack pointer +2, and its second one is at the stack pointer +1. Then the function can do everything it needs to, and then when it's ready to return, its return address will be at stack pointer +0, and it can return to the correct place in the program where it left off. Running now is a recursive version of the Fibonacci sequence. This requires a very deep recursion depth, so it's a good test on the stack, and it works perfectly and is probably my favorite program at this point. The last new module is an LCD display for more output capabilities. This module is actually pretty simple to operate. You write into one register for instructions, such as clear display, and then another register for data, so to print a character. So now you can print out pretty much anything you want, and I even created a program that takes a number, converts it to a string of characters, and then prints it. So that is it for this version of the computer. I'm always adding new features, currently looking at adding a compiler so that a proto version of C can be compiled and run on this computer. Other than that, I have a technical write-up that I'm updating as new features get added, and thank you for watching.